Today's lesson is part 2 of section 1.4, Building Functions from Functions. The first thing that we're going to talk about today is what's called a relation, which is just an ordered pair, example xy. We are going to use the idea of ordered pairs throughout this lesson today. The next thing we're going to talk about is what's called implicity, which is an equation with two functions that together would not be a function. The example I have here is x squared plus y squared equals 9. From earlier in the chapter, we learned that this is not a function because when we square y, that creates two separate functions. What we're going to do to show those two functions is solve for y. My first step is I'm going to subtract x squared to the right. So I get y squared equals 9 minus x squared. When I take the square root of both sides, that creates plus or minus the square root of 9 minus x squared, which creates our two separate equations. Y equals the square root of 9 minus x squared, and y equals negative the square root of 9 minus x squared. If you graph both of these equations together, it will be a circle. And as we know, a circle in itself is not a function, but if we separate the circle with a top half and bottom half, they are two separate functions. The big concept that we're going to discuss in this section is inverse relations and finding inverse functions. To do this, we are going to switch the x's and y's. So if I have an ordered pair AB, I'm going to change it to BA. An example could be 7, negative 3 is going to be switched to negative 3, 7. The notation that we are going to use is f to the power of negative 1. We describe this as the inverse of f. In your homework, you're going to be asked to find the inverse of different functions. So the first thing we're going to talk about is how to find the inverse of f of x equals x plus 2. Step 1. I'm going to take f of x and replace it with y. We learned early on that y and f of x are the same thing. And when we're dealing with inverse functions, we want to have a y and an x in the problem. The next is the process of switching our x's and y's. So wherever there is an x, I'm going to put a y. Wherever there's a y, I'm going to put an x. Then I'm going to solve for y. So if I solve the equation for y, I get y equals x minus 2. Again, all I did is I subtracted 2 to this side, but then I wanted y to be first, so I flipped everything to be y equals x minus 2. I would then put it into inverse notation, so the inverse of f equals x minus 2. Next here, I have another example that's a little bit more difficult than the previous page. The function that I'm going to do is f of x equals the square root of x minus 3. So the process is going to stay the same. Solving for y is going to be a little bit more confusing, but again, the steps in doing it is the same. Step 1, again, is replace f of x with y. So y equals the square root of x minus 3. The next step is I'm going to switch my x's and y's again. Again, notice where there is an x, I put a y. Where there was a y, I put an x. I put the right side on the left because when I solve for y, I want y on the left side anyway. So now the challenge becomes, how do we solve for y? First, I need to square both sides. By squaring both sides, I get rid of the square root on the left to get y minus 3 equals x squared. Last step, add 3 to both sides to get y equals x squared plus 3. And again, the answer in inverse notation is the inverse of f equals x squared plus 3. We will be doing a number of these examples in our homework. Again, the process is still the same. Switch your x's and y's and solve for y. The challenge will be, how do you solve for y? The next concept we're going to talk about is a one-to-one function. And what makes a function one-to-one? Here are the things that we have to have. First of all, an x is paired with a unique y, and vice versa, a y is paired with a unique x. This may sound confusing, so we're going to talk about this using a graph and using what's called the horizontal line test. It's different than the vertical line test. The vertical line test tells us if a function is a function. The horizontal line test tells us if a function is a one-to-one function. So an example could be, let's say I have a parabola, which we all know is a function. But if I draw in a horizontal line, you notice that the horizontal line is going to intersect the graph more than once, which tells me that this function is not one-to-one. If it is one-to-one, it will only intersect the graph once. So if it does it at anywhere in the graph, as you can see, it's going to do it in numerous places, which means that this function is not one-to-one. An example of a one-to-one function could be something like this, where a graph, again, if I look at the horizontal line, I'm only going to intersect this graph horizontally just once throughout the whole graph. There's never going to be a spot where it intersects twice. So this is an example of a one-to-one function. Again, both of these functions are functions, but only the red one is a one-to-one function. Reflections are very similar to inverse functions. We are just looking at switching the x's and the y's. If this happens, this tells us we do have a reflection over the line y equals x. Again, a simple example of this could be if you have an ordered pair 4, -2. If I switch that to -2, 4, that would be an example of points that are reflected over the y equals x. Just like we talked about odd functions. The last thing we're going to talk about here is another way to decide or figure out if two functions are one-to-one, or if a function is one-to-one. So the inverse composition rule says this: if f is one-to-one with g, then this happens. The function, the f of g equals x, and also the g of f equals x. Using the composition functions like we did in the early part of this section, we can determine if a function is one-to-one. Example. From earlier in this lesson, we had a function f of x equals x plus 2. I took the inverse of that, which happened to be x minus 2. Here I can show you that these are inverse or one-to-one functions. So what I did, if I take g and plug it into f, you will notice that the 2's will cancel out and you will get x. Just like if I take f and plug it into g, again, the 2's will cancel out and I will get x, which tells me that both of these functions are one-to-one, which does make sense because they're linear, and a linear function is going to be a one-to-one function. The homework for this section is going to be page 128, 28 to 30, and 40 through 60 even.